Hey guys, welcome to Safi Mixed. In this video, I'm talking about the effects of changing size of planets on the lengths of days on their surfaces. At the end, I will apply the results to the case of the Earth. That is, I will answer the question what would be the length of the day if somehow the Earth squeezes, thereby changing its radius to a new value. This, in fact, is a trivial problem in classical mechanics whose answer lies in the application of law of conservation of angular momentum. To understand the answer, let's go through this presentation. Since planets are more or less spherical in shapes, therefore, the angular momentum of spherical bodies is defined as the product of moment of inertia and angular speed. That is, I can write them as I times omega, where I stands for moment of inertia and is measured in kilogram meter squared, and omega is the angular speed measured in time inverse. Furthermore, most of the planets revolve about an axis passing their center, and the moment of inertia for spherical bodies through an axis passing their center is given by 2 divided by 5 times mass times square of the radius of the spherical body. If we substitute this value at this position, the angular momentum reduces to this form. Now, in the absence of external or perturbative forces, the angular momentum would remain constant. And if we look on the left side of this equation, there are three quantities: mass, radius, and the angular speed. If the mass also remains constant and somehow the size of the planet changes, that is the radius in this equation changes, in order to compensate the change in radius, the angular speed must change. And if that is the case, we consider that the radius changes from its original value r prime to a new value r prime, then the angular speed omega must change to a new value omega prime. So the new angular momentum with this substitution would become L prime equals 2 divided by 5 times m times square of the new radius r prime times the new angular speed. Now, in the absence of external forces, the law of conservation of momentum dictates that the momentum L of this planet must be equal to the momentum L prime. Using this condition, we can write this one equation under the conservation of angular momentum, and substituting this value for L prime and this value for L, we can put the equation into this one form. Now we can cancel this thing with this thing on the two sides and the mass with mass on either side, and can reparameterize the equation into this form, where I have taken the r prime to this side and have combined that with r in the form of a division and have taken square of the whole equation. Now we know that the angular speed is related to time period through this one equation. So if I substitute this form of omega and omega prime at this position and this position, I can put this equation into this one form, and I can again cancel this thing with this thing, and if I invert the equation, it can be written into this one form. That is, the time period is related, that is, the new time period is related to the old time period through the square of the ratio of the radii. Now, if I write the equation into this one form, then I make the ratio of time of the original time period and original radius, which defines the new time period in terms of the new radius. That means the new time periods of the planet is directly related to the square of the new radius. So if I use this equation and want to find the time period of the Earth for a change radius, that is, if the radius of the Earth reduces to half of its original radius r, what would be the length of the day on the surface of the earth? If I substitute this value for r prime at this position, I can write t prime, that is the new time period at the surface of the earth, into this one form. I can cancel this r squared with this r squared and can put the equation into this form. That is, the time period or the length of the day on the surface of the earth, if the radius reduces to half of the original radius, would reduce by 4. That is, and we know that this time period originally for the earth is 24 hours. So if I substitute 24 hours, that would leave the length of the day on the surface of the earth equal to 6 hours. So the law of conservation of momentum tells that the length of the day would change as the square of the radius of the planet. And if you haven't yet subscribed to SophieMax, kindly support the channel by pressing the subscribe button and also the like button on the video. Thanks for watching.